The received wisdom on how activity affects energy expenditure is that the more activity is undertaken, the more calories will have been burned by the end of the day. So, for example, if we go through a period of burning 300 kilocalories a day more on activity by committing to a daily exercise regime, we expect that by bedtime our total energy output for the day is 300 kilocalories more than it used to be. But research demonstrates that this isn't the case. Humans, like many other animals, can respond to long-term increases in energy expended on activity by reducing the energy expended on other processes of the body. Evidence is emerging that people exhibit energy compensation when expending energy at chronically high levels. However, it is unknown whether energy compensation occurs only under these extreme conditions, or at least only during periods of prescribed exercise, where measured or inferred energy compensation has been documented on a number of occasions, or instead whether it is the default model of energy expenditure in humans living typical lives who naturally adjust their activity and energy intake over time. In our study, we tested for energy compensation using the largest dataset on human energy expenditure ever assembled, where people were measured living their normal, typical lives. Understanding energy expenditure management by the body will provide key physiological information for managing human health. We analysed paired measurements of basal energy expenditure, the rate of energy expended just to keep the body ticking over, and total energy expenditure, all the energy burned every 24 hours, for 1,756 adults making use of the International Atomic Energy Agency doubly labelled water database. Controlling for people's age, sex and body composition, we conducted a multiple regression of total energy expenditure against basal energy expenditure. Unsurprisingly, this returned a positive relationship between the two. People with higher basal energy expenditures are therefore likely to have a higher total energy expenditures. However, the slope value was significantly less than 1, indicating a considerable degree of energy compensation. This phenomenon can be seen best by regressing activity energy expenditure against basal energy expenditure. Activity energy expenditure is here estimated as the difference between total and basal energy expenditure, while also accounting for the energy costs to ingest and digest food. This regression revealed a significant negative relationship. Higher rates of activity energy expenditure are associated with lower rates of basal energy expenditure. Thus, our data suggest that humans living typical modern lives exhibit a fairly strong compensation between the energy they expend on activity and the energy they expend on basal metabolic processes. Over the long term, more than a quarter of the extra calories burned by people during activity do not translate into extra calories expended that day. Presumably, such compensation would have been adaptive for our ancestors because it minimized food energy demands and hence reduced the time needed for foraging, the advantages of which may include reducing exposure to predation. However, it is potentially maladaptive for modern living humans exercising to try to burn off excess food consumption. Interestingly, details of our analyses indicate that the slope of the total energy expenditure basal energy expenditure and the activity energy expenditure basal energy expenditure relationships is lower in people with greater fat mass. In other words, energy compensation is higher in people with greater adipose tissue. People that are at the 10th percentile of the BMI distribution compensate for 29.7% of the calories spent on activity, whereas people at the 90th percentile compensate for 45.7% of their activity calories. If energy compensation has an underlying genetic basis, in the future it might be possible to screen individuals in order to ascertain whether exercise would be a valuable fat loss intervention because they are a weak compensator, or a fruitless fat loss intervention because they are a strong compensator. Moreover, we need to understand whether there are costs to reducing basal energy expenditure. If there are, such as for example a compromised immune system or slowed recovery from injury, then for some individuals the point at which exercise levels reach a detrimental level will be considerably lower than for others. If you'd like to find out more about this research, more analyses and data interpretation, and perhaps the details of the statistics we applied, you can access our paper published in Current Biology at the journal's website, or contact the corresponding author.